Okay, now let's consider the set of quadratic polynomials. The set of polynomials, we have a multiple of x squared, a multiple of x, and a constant number. And this set on the operations of addition of polynomials, and multiplication of polynomials by real numbers. Okay, now this does in fact constitute a vector space. We want to see how to prove that this constitutes a vector space. As you should know at this point, there are 10 axioms, basically 10 criteria, all of which need to be satisfied in order for something to represent a vector space, or to be a vector space. So my first question, is this closed under the operation being addition? Okay, so you always ask, is this set of whatever they are, polynomials, aardvarks, ordered triples of real numbers, and so forth, we have an operation, addition in this case, is that set closed on its operation? That is, if you combine two of them using the operation, do you get another one that's still in the same set? Because you don't want a set of things where you combine two of them and you're no longer in the set. Everything ceases to make sense if that's the case. Well, I say yes because why? Let's let a1x squared b1 plus b1x plus c1 be one of our quadratic polynomials, and a2x plus a2x squared plus b2x plus c2 the other. Okay, so now we've got two of them, we add them together, and what do we get? Well, very clearly, just simple algebra tells us that if we add this to this, we get a1 plus a2 quantity times x squared, quantity b1 plus b2 times x, quantity c1 plus c2. And that this then equals ax squared plus bx plus c, where a is a1 plus a2, b is b1 plus b2, c is c1 plus c2. Okay, but let's be careful. One part of the definition of quadratic polynomials is that all three of these numbers in every polynomial are real numbers. So a1, b1, c1 are real numbers, so are a2, b2, c2. Does it follow that a, b, and c here are real numbers? Well, sure. If a1 and a2 are real numbers, so is a1 plus a2, and a just represents a1 plus a2, so a is a real number. And the same with b. It's equal to b1 plus b2. Where did they come from? They came from here. These are coefficients in our polynomial, in our quadratic polynomial, so they are real numbers, so their sum is a real number, so b is a real number, and the same argument applies to the c. So we've established that the quadratic polynomials are closed, and let's celebrate by putting a little check mark next to the word closed. Now the next question I ask, and I did this intentionally, you can tell by the way the questions are phrased, next thing I ask is, do we have inverses? Okay? Now that was premature. If you understand what's going on here, you understand why this is premature. So think about why it would be premature to ask about inverses at this stage. Well, the next question we ask if there's an identity. And at this stage it occurs that, well, maybe we understood what we meant by inverses and so forth, but we hadn't identified an identity. And before you identify an identity, you can't really talk about the inverse. So I've switched the order of these two questions. One of the questions when we got to identity is, why was this and the preceding question in a very strange order? Well, that's the reason. You really have to talk about the identity before you can talk about inverses. Now you might assume what the identity is and then find out that you were right, which I think most people might do with these two questions, but you do want to ask the questions. You want to ask about identity before you ask about inverses. Okay, and we're talking about the identity for addition. I wasn't real specific about that. So the question then is, what do we add to a polynomial in order to get the same polynomial? If we got ax squared plus bx plus c, what polynomial do we add in order to get ax squared plus bx plus c? Well, there are ways we could do this. We could, let this be 3 additional unknowns, and this is going to have to be this minus this, and you're going to find out that it's just 0 and 0 and 0. Or you could just understand that, okay, obviously, if I add 0x squared plus 0x plus 0 to ax squared plus bx plus c, I'm going to get ax squared plus bx plus c. So the identity is 0x squared plus 0x plus 0, and we're going to use that in talking about inverses. Now, we also mentioned and note that we could talk about the representation of the ax squared plus bx plus c as just the column vector ABC, and we got to add something that gives us the column vector ABC. Well, in vector notation, we're pretty clear that it's got to be 0, 0, 0, because a plus 0 equals a, and so forth. Also up here, before I go on, we represented the same sum as in the vector, representing each polynomial as a column vector. We did the same thing that we did here, and that these are real numbers. And I didn't complete the thing, but we see how we could have written this out in terms of column vectors. Okay, well, let's look at inverses. What are inverses? They're a polynomial and its inverse are characterized by the fact that they add up to the identity. So here's one polynomial, a1x squared plus b1x plus c1. We add that to another polynomial, a2x squared plus b2x plus c2, and we get the identity. If this is the case, well, we can solve this easily enough. The only way this adds up to the identity is if a1 plus a2 equals 0, meaning that a2 is negative a1. And also b1 plus b2 has to be 0, so b2 equals negative b1. c1 plus c2 is 0, so c2 is negative c1. So we find that the inverse of a1x squared plus b1x plus c is negative a1x squared minus b1x minus c1. I don't think I said c1 when I read this one off, but you get it. So now we celebrate a little more. We check off identity and inverses. And then I say other questions. Okay? Now I'll expand on what we did in class just a little bit, but I'll do that in another video.